So here's your extra path length, and when it comes out, then you recombine them over here, and depending on the extra path length in here, if they come back in step, you've got a constructive interference. If they come back out of step, it's destructive. So you can get, the films look colored. If it comes, let's say the extra path length reconstructs for a red light, then you get a nice bright reddish hue on the film. Now the trick here, though, there's a little catch that you can work out, and that is that in here, see, you want n lambda. Well, what is lambda in this material? This is some kind of material like water, oil, film. So the lambda in the film is not exactly the same as the lambda in the air, because the velocity of light is slower in the film than in air. So in fact, the lambda in the film, let's say medium 1, medium 2, and this one has an index of refraction n, the lambda in the medium 2 is lambda in the air, or medium 1, over n. And remember we said the wavelength gets shorter. If you go to medium where it's slower, the wave catches up with you, and your wavelength gets shorter. So it's really the wavelength in the medium. And lambda in the air over the index of refraction has to be, say, a whole number of wavelengths to get, you would think, it would get you constructive interference. But there is a catch, and that is that the fact that when light reflects off a surface from a less dense or more dense medium, it changes its phase by 180 degrees. Because it may come in a peak, but it comes out a trough. So you have to add another half wavelength, lambda over n plus a half, plus lambda over 2. You have to add another half wavelength in this material to make up for the fact that there's a phase shift when you bounce off. When you come out, it's not off this surface, there's no change, off this surface is not, but there happens to be a change off this. So you end up with something like n lambda, how does it go now? This you have to be a little careful. Yeah, n lambda over 2 plus a half lambda is equal to, now if you're looking straight down on it, your path in this film is twice the distance. So that should be, okay, n. You have to get a certain, what you have to get is a certain number. This is the order. The order, that is how many, you have to get an integral number of wavelengths in medium 2 plus a half wavelength in medium 2 to give you twice the thickness. And then you just take medium 2 having wavelength air. Okay, so I'm sorry, this is really, I can pull out the lambda 2. I get 1, no, should be m. Should be m lambda over, okay, wait a second. Should be m lambda over 2 plus a half lambda over 2. This is what it should be, I think. So we pull out lambda 2, we get m plus a half will equal to 2d if you're looking straight down. And it says that this will give you constructive interference. And so let me put it where it's more clearly observable. So this is the order. This is the number of full wavelengths you have plus a half to account for that change in phase of reflection times lambda air. And then I put the index of refraction, n2, on the other side, because this was lambda in the medium, was equal to lambda air over n. So I substituted for lambda in the medium, put in lambda in the air, because that's what I know better, and put the index of refraction on the other side, n2. So again, though, I keep emphasizing that we're doing the same trick. We put in the light, it's coherent, we split it, we send a part of it on a different path, then we reunite them, and if you get them back in phase, you get a positive interference. Now, there's even more amazing, actually. Oh, well, here's one other little trick, the same trick again, where you can have two different media, and they have different indices of refraction, so the wavelength changes, so it slows the wave down, so when it comes out, it's a little bit behind the wave that went to a faster medium, and so that's another way of getting the waves to be out of phase, and when you add them up, you can get an interference effect. Same trick. You can play the same trick, though, even with a single slit. This is perhaps a little more strange, and that is that we can consider a single slit as a source of Huygens wavelets. This is a little less obvious, actually, or I'd say a lot less obvious, but the idea would be something like this. You have a single slit, and we have the wave coming in again. The wave is in here. And what we do is we think, again, now instead of thinking of the slit as being a point source, we're actually going to take into account that it has a finite size, which is usually that space between the slits, usually called d. The width of the slit is usually called a. And we're going to worry about the fact that the wave within a is a source of other wavelets. It's a little strange, actually, because this might be in a vacuum even. And so you wonder, what's shaking here? What's emitting these secondary wavelets? And I don't know that I really have a feeling for that, but it works. Let me just put it this way. The electric fields of this electromagnetic wave seem to radiate as though they were dipoles. And so they are themselves sources of Huygens wavelets, even within this slit. So a single slit will have a diffraction pattern. And it's very easy to calculate what it is, fortunately. We can do a very simple thing. Namely, suppose we put a screen over here, and I think you may well be doing this in the lab next week. The simple construction that you can make is, let me pair up little wavelets coming from this part of the wave with one that's coming a half of a slit width away. This one with this one. And let me just, this one is sending out its wavelet to someplace here. And this one here, half of the thickness away on the slit, is sending out its wavelet. And we play the same game. We think of it as two different beams coming from the same source, but this one has a slightly longer path length. So it has a delta L, extra path length, which is half this width times the sine of the angle. Delta L is equal to A over 2 times the sine of theta, where theta is the angle to this place where we're going to look at the pattern. So again, we play the same game. If this is a a full wavelength or some multiple of full wavelength, you will get a bright spot. But if it's n plus a half wavelength, if that path difference is that, then it will give you a dark place. Well, in the case of a single slit, we think of it as being typically a bright light coming through a single slit, so it's going to be bright. So what we'd be looking for really is where the first dark ring occurs. So that's what I think is calculated here, where this a over 2 sine theta is a half wavelength. That will be the first minimum. And so the formula for that is a sine theta is the first minimum equal lambda. Okay? So even a single slit or even a circular aperture can give you a bright spot with dark rings around it. Sounds like after a night of studying in your eyes. Anyhow, the second minimum would be, you could find that too, but then what you would do is to maybe divide the thing into 4 parts, and you match this part with this part and find where it constructively interferes, and so on. So you can find the successive minima, dark rings. Okay. So in any case, when you look at this formula, you realize that the angle at which the thing occurs is basically lambda over a, where the rings occur. So as you make if you make the slit smaller, the angle gets larger. See, this is a peculiar thing. If you try to take light and you try to confine it to something by passing it through a slit, if you make the slit of the order of the wavelength, instead of confining it, you actually blow it up. What happens is, as you make a smaller, the angle at which it deflects increases, sine theta increases. So that's what this set of pictures is trying to show. Here, when you have the spacing, it's 10 times the wavelength, you have a nice sharp edge. When the wavelength is closer to the size of the aperture, you notice how it broadens, and when a is lambda, it's broadened further. So this has actually some considerable consequences. But I did want to show you, yes, ma'am. Well, the truth is that these slits will be very small, and the distance will be large, so it really won't make any difference. The wavelength of light is extremely short, so if you have a slit about like that and you have your screen over here, it really won't make any difference what you think. But to the light it makes a difference because the light wavelength is so short that even that slight difference will make it in step or out of step. But the angle will be approximately the same. Not exactly, but close enough for this purpose. Top or the bottom, right. My scale here is way off because it's, we're talking about thousands of lines per inch. Could you imagine we have a 10,000th of an inch between lines, and then you put a screen, say, a meter away or a couple of feet. So the difference between the top and the bottom of that slit and a meter away is not much. It's a very good point. This picture is somewhat deceptive. There was another question now? Okay. Now, there's a very fun demo here that I should do, which is, let me see, there's Babinet's principle, which you're going to use in the lab, which I wanted to tell you about before you got in there because it's a little puzzling. But this is an interesting case. This is kind of a single aperture, this big hole here. And let me turn it on. Let's see. Yep, let it warm up. Again, we're using here microwaves. The microwave tube is here. It's an electromagnetic wave coming across when it warms up, coming out of a horn, projecting through this aperture. I won't overdo it. Okay, now this seems pretty sensible. There's a big hole, and the wavelength is about like that, so it's not surprising the waves can come through. Now you would think that if I make the hole smaller, the amplitude, let me turn it up so you can hear it more dramatically. Let me know when it hurts. Okay, as I make it smaller, it actually gets larger. And then smaller. That sounds sensible. I'm cutting it off, right? But it comes back. And then finally, if I squeeze it down enough, it doesn't go through. It's kind of weird. But that's an interference effect that's going on. Let's go backwards then. This is sensible, it's getting more. Now it's getting less. Even though I'm making it bigger, it's getting less. More, that's reasonable. But even making more, it gets less. That's an interesting effect. Huh? So I want to show you that because it's a little odd, but it's understandable. See, we have something like this. It's again the same kind of story. The way to look at it, let's see if we can figure it out. We have this big thing. So the waves are coming through. Now the way to look at it is that if I divide this up into, actually there's an official word for zones, of sort of equal area, so that the same amount of energy is coming through these areas. And if each of the areas, and here's my receiver, if, for example, this zone is a half wavelength further away than this zone, these two will cancel. And suppose this one, so let me try to do it this way. This is in phase, and these ones are sort of out of phase. But let's say they have equal area so that they can really cancel out. So what you can see is that as I close this down, it's a competition between how many, let's say I start out with cancellation. In other words, in this picture here, I have as many in phase, out of, this cancels this cancels this. So I should get 0. Now if I close it down, I cut off this one, so I have in phase, out of phase, and I have a net in phase. So by closing it down, I get more. See that? If this produces in phase, this produces out of phase, in phase, out of phase, when I close down, I get rid of this one. And so I'm left with in phase, out of phase, in phase. I have a net in phase, so I have a net signal here. And if I close it down even more, then I cancel this one out. See, and then I should get another null. See how that might work? It's really quite cute. All right, now, do I have time for Babinet? Easy cabinet, 2 minutes. Well, all right, let's throw it out here. This is fun. The idea is you're going to go into the lab, and they're going to say, okay, we know the story. If you have a single slit, sort of like what we did here, you can get a diffraction pattern from the single slit because you can pair up points here with points here, and if they're half wavelength separated, they will cancel, and you get a dark spot. So your pattern will look something like this. You'll have a dark spot someplace. Okay, that's with a slit. Now they're going to argue, suppose I replace the slit with a solid object. They're going to ask you to pluck a hair out of your head and paste it on a thing, and that's going to be your simulation of the opposite of a slit, an anti-slit, okay, if you will. So what they're going to say is, instead of having a slit, let me have an opaque something, and I shine a light on this. And what is the diffraction pattern produced by this thing? An opaque thing. And they're going to say that the opaque thing of the same size will give you the same diffraction pattern as the slit of the same size. That's what you're going to do in the lab. It's another one of these remarkable things. And here's the kind of proof of it. It's called Babinet's principle. They don't use that word either in the book or in the lab discussion, but I heard of it before, and so Michael passed it on. It's another Frenchman strikes again. So the argument is, what is the theorem? So it says this, that if I take an opaque thing and I cut out a shape, so I have an aperture, and I also have the thing I cut out, which is opaque, then if I shine light through this aperture thing, I'll get a diffraction pattern because light will diffract around it. Okay, it says that the diffraction I get from that hole will be the same as what I get from the cut out solid piece. When I look over here, see where the light diffracts? And the proof is actually rather straightforward. It's given here. It's in your notes, so if you don't get it, you can just look at it. The idea is you start out with a beam of light, like a laser beam, and there's a place where the laser does not go. It's point P. It's outside the beam. But when you put the cutout thing here, because of the diffraction of the edge, the Huygens thing, the light will propagate out, and some light will appear at P. Okay, good. Okay, now you put in a sense, the anti-slit, or the piece you cut out. Now it will also produce light at P because it's diffracting also. But the sum of these two, the sum of this whole, plus, you see all of this stuff here, the light is coming through, so the sum of this plus this is this. See that? Here's a free space. Here's the free space of this one. If you add up the free space of this and the free space of this, it's the free space you started with. So the sum of this plus this should give you this, meaning no light. So that says that when you have this one, the light here must have the electric field just equal and opposite to the first one. So the light due to this one should be minus the light due to that, but the intensity is the square, so that minus doesn't count. So the amount, the diffraction that you see here due to this cutout will be the same as through the aperture. Isn't that cute? Monsieur Babinet? No. Très bien. Très bien fait. So that's Babinet's principle, and you will do that. Presumably you'll have a slit and see the diffraction pattern, then you'll pluck a hair, and it should give you pretty much the same diffraction pattern because of Babinet's cabinet. Okay, have a good weekend.